Morning everyone. My name is Pranav and I am from Institute of Aeronautical Engineering IARA. So today's subject is matrices and calculus, and today I am gonna talk about one of the interesting topic in matrices and calculus. It is nothing but simply invertible vertices. So matrices play a vital role in engineering mathematics and linear algebra. An invertible matrix, also called a non-singular matrix, is one that has an inverse. The inverse helps in solving of linear equations, transforming coordinates, and many real-world engineering applications. So, matrices plays an important role in engineering mathematics. So, consider a square matrix A is said to be invertible if there exists another matrix B such that A cross B equal to B cross A equal to IA, where I is the identity matrix. In this case, B is called inverse of A and is denoted by A inverse. For a matrix A to be invertible, A must be a square matrix. The determinant of A, that is det A, must be non-zero. If det A is equal to 0, it is singular matrix, so it is non-invertible. And if det A is not equal to 0, it is not singular matrix and it is invertible. So it's like if we consider a matrix of 2 cross 2 or any of the matrix, if the det of A is equal to 0, it is non-invertible, and det of A it is not equal to 0, or then it is non-singular matrix, so it is considered as invertible matrix. Next, formula of 2 cross 2 matrix inverse. For 2 cross 2 matrix, consider a matrix A B C D. A equal to, begin a B matrix A and B, C and D, A equal to A C B D. Then A minus 1 equal to 1 into AD minus BC into D minus B minus CA into A power minus 1 equal to fraction of 1 into AD minus BC, and begin with D and minus B and C minus C and A and B matrix, and A minus 1 equal to A minus 1 equal to AD minus BC into 1 into D minus C minus BA. Then condition is AD minus BC is not equal to 0 and AD minus BC is equal to 0, AD minus BC equal to 0. So here we can also see the example of 2 cross 2 matrix given A equal to 2 3 1 4, which is a matrix, and B matrix is A equal to 2 1 3 4. So the determinant of the matrix A is which we can do as 2 into 4 minus 3 into 1 equal to 8 minus 3 equal to 5. Now A minus 1 equal to 15 into 4 minus 3 minus 12 into A power minus 1, and it is fraction of 1 into 5, 4 and minus 3 minus 1 and 2. Now A minus 1 equal to 51 into 4 minus 1 minus 32, where A minus 1 is equal to 0.8 minus 0.6 minus 0.20.4 into A power minus 1, and A minus 1 is equal to 0.8 minus 0.2 minus 0.60.4, inverse of 3 cross 2 matrix. So for 2 cross 2 matrix it is different, and for 3 cross 3 matrix it is different. Steps for 3 cross 3 matrix A: compute determinant det A, find minor matrix determinant of 2 cross 2 submatrices, apply cofactor signs, take transpose, adjugate matrix adjacent of A. Formula: A minus 1 equal to 1 of mod A into adjacent of A into A power minus 1 equal to 1 of det A, and C dot adjacent of A into A minus 1 equal to det A into 1 into adjoint of A. Tip: for engineering exams, remember determinant first, then adjoint divided by determinant. So in 3 cross 3 matrix, first we should take submatrices and find their determinant first. Then we should find their adjoint. Then we should divide it by determinant. Now, example for 3 cross 3 matrix is, consider a matrix 1 2 3 0 1 4 and 5 6 0. Now, we can use the formula BAX equal to B equal to X equal to A minus 1B, and also control engineering in transfer functions and state and space methods. It is also used in electrical circuits, solving multiple network equations, computer graphics, undo transformations like rotation, scaling, and also used in robotics. And also it is used in signal processing. So these are the like an applications of invertible matrix where we can use it in control engineering for transfer functions and state space models, and also in electrical circuits solving multiple network equations, and also in computer graphics to undo transformations like rotating and scaling, also used in robotics to find the inverse in kinematics for robotic arms, and also in signal processing. Now, methods to compute inverse. First one is analytical formula, which is basically used for 2 cross 2 and 3 cross 3 matrices. And second one is Gauss-Jordan elimination for large matrices. Third one is argument with identity matrix, row operations, and reduced to identity and argumented side equal to inverse. Fourth one is LU decomposition for engineering and numeric methods. So basically there are 4 methods. One is for 2 cross basic 2 cross 2 and 3 cross 3 matrices, and second one is Gauss-Jordan elimination, which is mainly for larger matrices, and third one is for argument with identity matrix, in which we use row operations and identity argumented side, and fourth is LU decomposition, which is used rarely but it is used in engineering and numerical methods. Now, coming to Gauss-Jordan elimination, the Gauss-Jordan elimination is a direct method used to compute the inverse a matrix without calculating the determinant. The procedure is: form an augmented matrix A by I. Apply row operations to transform the left part A into the identity matrix I. The right part will automatically become A minus 1 into A power minus 1 into A minus 1. The advantages of this is works for all square matrices. It reduces computational error and also preferred in computer algorithms and large system. So basically Gauss-Jordan method is like it is used to compute the inverse of the matrix by A minus 1, A power minus 1, A minus 1 formula. Also there are number of advantages with it. It works for all square matrices, reduces computational error, preferred in computer algorithms and large systems. Coming to LU decomposition, this LU method decomposes matrix A into two matrices, A equal to L into UA equal to L C dot UA equal to L dot U, where L is lower triangular matrix, U is an upper triangular matrix. Once decomposed, we can easily find A minus 1 equal to U minus 1 dot L minus 1 into A power minus 1 equal to U power minus 1, and C dot L power 1 A minus 1 equal to U minus 1 into L minus 1. It is basically used in numerical analysis, finite element methods, and simulation software like MATLAB. So basically this LU decomposition we can use in engineering mathematics and numerical problem solving. Here we use a formula A equal to L dot UA, where L is considered as lower triangular matrix and U is considered as an upper triangular matrix. In numerical computation, matrix inversion can be unstable if det A is very small. Engineers use the condition number con of A to measure how sensitive inverse is to small changes. If condition A is large, the matrix is ill-contained, which means inverse unreliable. If condition A equal to 1, the matrix is well contained. So the condition number con of A is like if it is large, the matrix will be ill-contained, means inverse is not possible, inverse is unavailable. If condition is equal to 1, the matrix is well contained, means the condition number should not be too high or too low, it should be equal to 1. Now, applications of invertible matrices in engineering. First one is for solving linear equation. The system Ax equal to Bax equal to Bx equal to B can be solved using x equal to a minus 1 bx equal to a power minus 1 bx equal to a minus 1b used in circuit analysis, mechanical equilibrium problems and network flows. And B is control systems used in state space representation where x equal to ax plus bu by dot x equal to x plus bux equal to ax plus bu. Inverse matrices are used to compute the feedback gains and transfer functions. C is structural analysis. Basically, it is used in civil and mechanical engineering. Inverse matrices are used in stiffness matrix methods and finite element analysis FEA. And D is in electrical networks to find current and voltage in multi-loop circuits using mesh and node. So basically, invertible matrices are not only used in maths, it is also used in real-time applications. We just now saw in solving linear equations, in control systems, in structural analysis, in electrical networks. And also it is used in robotics and graphics. In robotics, the inverse transformation matrix helps calculate the joint positions for a given end effector position. In computer graphics, it helps to reverse transformations, rotation, scaling and translation. So it is also used in robotics and graphics, which is like a real-time application for the students. Now coming to the common errors, the first error is forgetting to divide by determinant in adjoint method. Second is sign mistakes in cofactor computation. Third one is confusing minors with cofactors. Fourth one is not transposing cofactor matrix. Fifth one is attempting to invert on non-square matrix. Sixth one is ignoring that t equal to 0 and non-inverse exists. So basically these are the errors done by student while finding invertible of matrix. The first one is like you can't find forgetting to divide the determinant with adjoint method. Second one is sign mistakes, you write like plus minus confusing like that. And third one is like confusing minus with cofactors. Fourth one is not transposing cofactor matrix. And fifth one is attempting to invert a non-square matrix, ignoring that t is equal to non-zero which no inverse exists. It's like many of the students forgot if delta is equal to 0, then it's like inverse doesn't exist. But many of the students forget it and try to still find the inverse, which we can't get. Coming to the conclusion, invertible matrices are one of the most important mathematical tools for engineers. They provide a way to reverse process, solve complex systems of equations, and model real-world systems effectively. Understanding their computation methods, theoretical foundation, and applications helps in mastering linear algebra, which forms the core of engineering mathematics. Before attempting inversion, always check the determinant and ensure the matrix has full rank to avoid errors and instability. Thank you.